All right, good afternoon. Let's get started. So first of all, I posted, I think I did, I posted exam 1 and 2. If you have any questions, feel free to send me an email after class and I'll take a look at the issue. We should mostly just check if the points add up correctly or if there's any issues with the grading. If there's anything that doesn't make any sense to you, just let me know. We can look at it together. Just a reminder that we're going to have a quiz today, which probably going to be towards the end of the class today. And next Monday, so the coming up Monday, let's see, double check the calendar. Yep. So this is the second to the last week of this class. The following week will be the last. So next week will be the last week. We're going to have exam 3 on Monday. So exam 3 on Monday, 22nd. And again, it's just like the previous 2 exams. It only covers the material that from exam 2 to whatever we talk about this week. So that will be exam 3, and then after that we still have a few days, Wednesday and a Thursday, 2 days of classes, and a note that's a homework. So final homework. So there's a homework this week that was due Sunday, but there's another homework. So final homework due 26th, Friday. It's not going to be due the Sunday because I have to submit the grades on Friday night. If that homework has to be completed before Friday night. Due Friday, 26th at 8 p.m. And I want to point out that no extension for this homework allowed. So you have to plan your time well for this final homework. It's not going to be long. It's going to be, well, I hope it will be reasonably short, but it's not going to be like, 2 problems. It's definitely going to require some attention, but it's not going to be as long as the previous problem sets. So that's the final homework. Make sure you pay attention to the due date. There's absolutely no extension, unfortunately, because it's not up for me to decide. The math department and also the registrar office, they require the grades to be submitted on Friday by the end of the day. Okay, and exam 3 obviously will be graded before that. So I'll try to grade the exam 3 either Tuesday or Wednesday, and so you can take a look at the grading and then let me know if that's an issue. All right, any questions related to the quiz, exam 3, and the final homework? So I know some of you have to work, you might have travel plans, but whatever it is, you have to make it. You have to find time to complete the final homework. That's just my last message. So if you used to do homework on Saturday, you need to change your plan for the final week. Okay, all right. Any questions? I know Tim probably have some questions from reviewing for the quiz today. All right, so now let's spend some time going over the quiz review questions. Go ahead, please, Tim. Or anyone else?
Yeah, I just had one question about how you would set up the ones where it's a right triangle and it gives you 2 of the angles, and then you have to find the hypotenuse, and as well as the final angle up top.
Yep.
I was just wondering how you would, like, I tried the formula and for some reason I kept getting the wrong answers for the final degree angle.
Okay, is this going to be a, so let's see, is this going to be a calculate aloud problem?
I'm unsure about that.
Okay, well, let's just say, take this example. Let's suppose we know let's say we know this angle at the bottom right corner here. Let's see, that's going to be 20 degrees, for example. And in order to find the hypotenuse, we have to know one side.
No, both sides are given.
Both legs are given. Okay, so let's see. This is well, 20 is probably not a good angle because I don't know the correct side ratio. This is all right. So let's just see. This is 5. That's one side. Now the other side, we could find it by using SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Let's just see we were looking for this side. Suppose it's not given when we look for it, right? So if we look at the angle 20, now the angle 90, the right angle, basically it's useless. It's not going to help us at all. So we're going to use the angle 20 degrees. And the side, the legs that we don't know with a question mark, so that's opposite to the angle. And the side 5, that's going to be adjacent. So we have the opposites that we don't know, but we have the adjacent and the angle. So there's like an opposite adjacent with the angle. So that means we're going to use tangent. So tangent 20 degrees is equal to opposite, which we don't know, but adjacent we know is 5. So from here we can multiply by 5 on both sides to get the opposite side, which is going to be 5 multiplied by tangent of 20 degrees. If we have a calculator, we can get a good estimate. So that's the opposite. And now we have the opposite and the adjacent. We can use Pythagorean theorem to find the hypotenuse. I suppose we don't want to use Pythagorean theorem. We just want to use trig again. So this is the hypotenuse I'm looking for. And this is the adjacent side to 20 degrees. And we have adjacent hypotenuse and the angle. So that means we're going to use cosine. So cosine 20 degrees is equal to adjacent, which is 5, divided by hypotenuse, which we don't know. So from here, we can multiply by the hypotenuse. So we get whatever the hypotenuse is we're looking for times cosine 20 degrees is equal to 5. And we're going to divide by cosine 20 degrees. We just treat this as a number that we know. So hypotenuse equals 5 divided by cosine 20 degrees. And again, with the calculator, we know what the estimate should be. All right, so that's to find the missing side if we have an angle and a side given in a right triangle. Now, how do we find this angle that's missing at the top? Well, in order to find this angle, that's actually an easier way, which is using the sum of interior angles of a right triangle or of any triangle. So sum of interior angles of a triangle, which is going to be 180 degrees or pi radians. I'm putting pi radians here just in case, suppose we weren't given 20 degrees, we given pi over 9 degrees. I mean pi over 9 radians. That way you can use pi radians instead of 180 degrees. So here we have 90 degrees plus 20 degrees plus the missing angle, let's call it theta, which is going to be equal to 180 degrees. And then we subtract 90 and 20, so we get theta. So if you're looking for a missing angle, suppose there's at least 2 angles are given in a triangle, then it's a lot easier to use this approach. All right, any other questions on this particular example or anything else? Tim, did that answer your question?
Yes, it does. Thank you.
Yep, no problem. Anything else? Okay, let's see. All right, if you don't have more questions, I think. All right, if you don't have more questions, I'm going to move on with today's material. So we're going to begin talking about inverse trig functions, and I'm pretty confident that you all have seen it in the past, like inverse sine or arc sine. So those are inverse trig functions. So inverse trig functions. The benefit of having them is that, for example, we know sine of 30 degrees or pi over 6 is equal to 1/2, right? We have a sine of an angle. So this is the angle. This is the ratio, the trig ratio. So trig, sine, cosine, tangent, they always give a ratio of corresponding sides. Suppose we know this, right? It's easy. Sine 30 degrees equals 1/2. Well, how do we describe this angle in terms of the ratio 1/2? So if I want to solve for the angle, what I have to do is I have to isolate the angle. So the easiest way to do is to add a inverse sine to both sides. So sine to the -1. So on the left side, inverse sine and a sine, they kind of undo each other, kind of like square root and a square. So that just cancels. Give us 30 degrees is equal to inverse sine of 1/2. So as you can see, in the inverse sine function, you always put the ratio inside. And what we end up with is going to be the angle. And this is particularly useful if we know the ratio, the trig ratio, but we don't know the angle. So suppose there's something that we don't know the angle, but we know the ratio. So suppose sine of some angle theta is equal to, let's see, 11/20. And we don't know how big the angle is. Can we find the angle? That's why we need to use the inverse sine. All right. So just to kind of recap what we talked about here. So for the trig functions, like sine, cosine, tangent, etc. The domain is always going to be the angle measure. So what we put into the function is always going to be the angles. And in the range, what we get out of it, or the output, is always going to be a ratio. So this is the inputs. This is the outputs. So whenever you look at the trig function, you wonder what does the number we get from sine 20 degrees or sine 30 degrees. It's always a trig ratio. But for inverse trig functions, like the one I wrote earlier, for example, inverse sine or inverse cosine, etc. The value that we put into the parentheses, put inside the inverse sine, that's always going to be a ratio. It's never going to be an angle measure. You don't put an angle measure into the inverse sine. But what we get out of the inverse sine at the end is going to be an angle measure. So you have to know, if you see the notation sine of pi, for example, so sine, not sine pi, just say sine of 2. Nothing else given, right? So if you see something like this, you should immediately know that, because the number inside the sine is always going to be the angle. So 2 refer to not 2 degrees, but 2 radians angle. And what we get out of the sine of 2 is going to be a ratio, whatever that is. I don't know. We might have to put into the calculator to get the number. But if you see something like an inverse sine of, let's say, 1/7, and immediately you should tell yourself, oh, this 1/7 is not going to be the angle, it's actually a ratio. And what we get out of this on the right-hand side, that's going to be an angle. So it's just something to keep in mind. When you see sine and the inverse sine, you have to know which one it is, which one we're looking for, and what information do we have. And a side note here, inverse sine, or I'm going to write it later, is not the same thing as 1/sine. So that's the difference.
I have a question.
Okay, go ahead.
So if you're putting this into like a calculator to figure it out, do you
Yep.
have to switch between degree and radian mode?
Correct. So let's just say you're using the calculator to find sine 2, right?
Yeah.
Sine of 2. Because it doesn't say 2 degrees, so we have to assume it means 2 radians. So before you type that into the, let's say, a graphing calculator you have to make sure the calculator itself is in the radian mode.
Okay. And then for the sine -1,
So
it
that
would be
one,
degree mode.
it doesn't matter. So that one, it could be in any mode. It's just that at the end, let's just say you put this into the calculator. I don't know what it gives. Let's say it gives, let's say it gives, that's actually a good point. I don't know what it give you, but let's say it give you like 1/7 is about not even 0.5, 0.2. Let's say it gives you maybe 1, right? So that, if it just give you 1 at the end, that's very likely to be in radians, but you want to be double check, look at the calculator, see what mode it is in. If the calculator is in radian mode, the answer will be in radians. If the calculator is set to be in degree mode, then the answer will be degrees. But you don't have to change any of that. So either answer is fine. It's just that you have to know what the unit is.
Okay, that makes sense.
Yep. Good.
Thank you.
Good question. All right. So again, when you type this in, type sine or cosine, when you try to find the ratio, you have to be careful what the mode the calculator is set, and it agrees with the unit you put in. But when you look for the angle, it doesn't matter what the mode it is, it just, you get the correct angle corresponding to the calculator setting. Generally speaking, let's say you use the inverse sine function to find the angle, and you end up with, let's say you type something in there, you end up with like 20 or 30 or 50, maybe 100. So that's basically, that means degrees, right? But if you end up with something like, basically something between 0 and 2 pi, which you're probably not going to get, probably between 0 to pi or negative pi over 2 to pi over 2. So that's just going to be from 0 to 3.14, or maybe negative 1.7 to positive 1.7. That's very likely it's going to be the radians, because the numbers are a lot smaller in radians. If it's degrees, then you're going to have numbers like 10, 20, a lot bigger angles. All right, so let me give you the definition of sine of the inverse functions. So definition, so y equals inverse sine of x means, so if you see this, so that means, well, before I talk about the meaning, so this x is going to be the ratio, and this y is going to be the angle. So this equation implies that the x is equal to sine of y, because if y is the angle, we take sine of it, we get a ratio. So x is the ratio. Now the equivalent notation to y equals inverse sine of x is called arcsine. Y equals arc, arc sine of x. So arcsine and inverse sine, they mean the same thing. And this function has a domain. So it has domain, which is going to be, so the input is always going to be from -1 to 1. So if we put 5 into inverse sine, we get a problem. So for example, inverse sine of 5 does not exist. It's not defined. Whatever we put into the ratio itself has to be from -1 to 1. And I always think about either the unit circle, right? The signs of y coordinate, it never go beyond 1 or below -1. So the y coordinates of any angle is always going to be between those two maximum minimum values. And the range, remember the range we get is going to be the angle. Now the angle is not going to be just any angle. The range is only going to be from this angle at the bottom. So this angle, that's a negative pi over 2 to positive pi over 2. So you can consider the right half of the circle. So that's a range. That's the angle we're going to get by definition of inverse sine. And you probably say, oh, in the past we got, when we find the angle, we got like angle that's not in this, that's fine. But if we just use inverse sine directly, we should get the angle in this range. Kind of like when we find a square root of 4, we only can end up with the 2. We're not going to end up with -2. By definition of square root, you always have a positive value. But sometimes when we solve like x squared equals 4, we take square root, then we have to plus minus square root of 4. So that's something we added to it, but by definition of square root, it's always going to be positive. Same thing with inverse sine here. By definition, we only can end up with the output that's from negative pi over 2 to positive pi over 2. And then the next one is inverse cosine. Y equals inverse cosine of x, or sometimes we write arc cosine of x. So that means or implies that x is equal to cosine of y. And again, the y here is the angle. And the x is the ratio, it's the number that we put in. And this function has a domain just like the sine function. We look at the y coordinate cannot go above 1 or below -1. For cosine, it's the x coordinate on the unit circle. As you know, for x coordinate, the biggest x we get is 1, the smallest x is -1. So the domain, just like the sine, is going from -1 to +1. The range, however, is different. So the range is going to go from 0 radians, go all the way to pi radians. So that's a 0, that's a pi. So it's going to be the top half, 0 to pi radians. So that's the inverse cosine. And the next one is inverse tangent. Or you can see it as arctangent of x. So that means x equals tangent y. Now, if let's just say for today and tomorrow, if the inverse function looks confusing to you when you see it, just try to convert it into the trig function, sine, cosine, tangent, to help you understand it. But over time, you will understand it better. When you see it, you know what it's really looking for. It has the domain. Now, for tangent function, the ratio that we put in there is actually from -infinity to infinity. We can put any number in there. Now, the way I think about it is actually looking at the graph of tangent. So this is pi over 2. This is a -pi over 2. It goes like this. The ratio is the y value corresponding to this graph, and then the y value could go to infinity or -infinity because it continues in both directions. So that's why the ratio in this case becomes the input in the domain. So it's from -infinity to infinity, and then the range is going to be just like this piece I'm drawing. I'm not drawing other pieces. By definition of inverse tangent, or arctan, the range is from negative pi over 2 to pi over 2, and it does not include those two. Different from sine. So sine actually including those two ending values. For inverse tan, it does not include them because those two values corresponding cosine equals 0, which we cannot divide by 0 in the tangent. All right, so those are just a definition. I really recommend that you pay attention to them and then know them. That way you avoid a lot of mistakes. But I'm pretty sure you all saying it in the past. And the one final comment was inverse functions. So note sine, inverse sine of x, so sine to the -1 of x is not the same as 1 over sine of x. Now you all know what 1 over sine is, right? That's cosecant, which is cosecant x. So cosecant is 1 over sine, the reciprocal of sine. But inverse sine, even if we put the -1 in the exponent, it does not mean cosecant. They're different. So one is the inverse function, one is a reciprocal of the function. So they're not the same. Same thing with inverse cosine and the inverse tangent. They're not the same. So be careful there. When you see them, don't get confused. All right, so let's look at a few examples. So find inverse sine of, let's see, √2 over 2. So here I have inverse sine of √2 over 2. And then remember that this refers to the ratio, and what we're looking for is the angle. So there are a couple of ways you can call this x and think, okay, that's converted to different equations. So sine of what angle x give me √2 over 2. And if you have it memorized, then you know that pi over 4, right? Or 45 degrees. So x equals pi over 4 or 45 degrees. So based on memorization. And to be honest, with non-calculated sections, the inverse sine, the inverse cosine, or inverse tangent is always going to come up to be pi over 4, pi over 3, pi over 6, or multiples of them. You just have to know exactly which angle it is. It's not going to end up with the angle that we're not familiar with. In that case, we just use a calculator. But it's always going to be one of the multiples of those 3 common angles. So that's one way. Another way that I like to approach this problem is that I know the ratio is √2 over 2. So that means, remember, sine, it's going to be the y coordinate. So here I know that y coordinate of a point on a circle it's going to be √2 over 2. So that's what I already know, and I'm looking for x. Sorry, I'm not looking for the x coordinate. We're looking for the angle corresponding to that different x. So looking for this x, which is the angle. So what I do is I'm just going to draw a unit circle, do my best. And I know the y coordinate is √2 over 2. So this is a 1. It's definitely not 1/2. That's 1/2. This is √2 over 2. It's a little bit more than 1. So it looks like it's going to be, so that's my y coordinate is √2 over 2. So it looks like that's going to be the angle I'm looking for, or maybe this one. Which one is it? So now I got 2 angles I have to decide. One is in the first quadrant, one is in the second quadrant, both corresponding to the same y coordinate, √2 over 2. By just looking at it, I know it's not going to be some crazy angle, right? It has to be one of those 3 good angles. Well, immediately I know this one is going to be pi over 4 because it looks like it's halfway between 0 and 90 degrees. And there's the one in the second quadrant, I know that's pi over 4, 2 pi over 4, this is 3 pi over 4. Both of them is going to give me the same y coordinate, √2 over 2, but which one do I use? So here we have to go back to the definition. So inverse sine only going to give me angle from negative pi over 2 to positive pi over 2 in the right half. So I'm actually looking for angle in this right half of the circle. So the only angle I have in that part is pi over 4. So x equals pi over 4. So that's the way I try to think about this problem by using the unit circle. It works well for a lot of problems, but obviously it's, you kind of have to really know the angles very well and then know the, where root 2 over 2 is, the ratios. But either approach is fine. All right, so here's the second example. Find inverse cosine of -1/2. So again, you could rewrite this in terms of, let's just say this is the angle x. So we're looking for this x value. You can write as cosine x equals -1/2 and then try to get the x from here based on what you memorized. Or I'm going to use my approach. So cosine represents the x coordinate. So I know the x coordinate. So this is the ratio. So I know the x coordinate is equal to -1/2. So I'm going to draw a unit circle, do my best. And I know that this is the x coordinate, -1/2. So this is -1, 0, 1. -1/2 is right here. So if I go from there, draw a dotted line to the circle, looks like it's this angle or this one. In the second or third quadrant, that will give me -1/2 as the x coordinate. And from here, I can figure out the angle here. Well, how big is this angle? Well, if I'm drawing it, more or less accurate, clearly this angle between the terminal side and then the y-axis is a lot smaller than the other part between the side to the x-axis. So they're not the same. So it's not going to be 45, 45. So it has to be 30, 60. Which one is 30? I'm going to have to decide that this is 30 because it's smaller. The bigger one is 60. And now I just need to know how big is this angle from here to there. That's going to be 90 plus 30. So that's 120 degrees, or pi over 2 plus pi over 6. So 120 degrees or 2 pi over 3. Right? Now, what about the angle in the third quadrant? Well, that's going to be here by just eyeballing it. We know that this is a small angle. The one that between the terminal side and the x-axis, that's a big one. So this is going to be 30. This is going to be 60. So I'm going to take 180 plus 60. So that's going to be 240 degrees. Or we can write it using the radians. So that's going to be pi, 3 pi, pi, and then another pi over 3. So that's 3 pi over 3. So that's going to be 4 pi over 3. So that's how I choose to solve those problems, by just looking sort of like looking at the circle, looking at the geometry, the triangle. Okay, so now we get two angles. Which one is the correct one, right? We don't know. Well, by definition of inverse cosine, the angle, the output has to be from 0 to pi, the top half of the circle. So I'm going to pick the angle in the top half of the circle, which is going to be 2 pi over 3. Okay, any questions on those two examples? I personally find it easier, especially when you are given a ratio that's not familiar. For example, -1/2, right? I mean, obviously you could think, oh, isn't that related to cosine 30 degrees equals 1? Sorry, cosine 60 degrees equals 1/2, which is true, but the negative make it difficult to sort of figure out what the angle is. I always find that unit circle is easy because if you graph the x coordinate, you immediately know where the angle is going to be, either in the second or third quadrant. Then you just have to decide how big it is, how big is the angle by thinking about the triangle size or the angle size. It's always going to be multiples between 30, 45, and 60. Okay, so let's look at another example. We're going to solve this right triangle. that has two sides. Only two sides are known. Oh, by the way, what I'm talking about today, that's not going to be on the quiz, right? So except for the first example that could be on the quiz, doesn't mean it has to be, could be. The inverse functions from here to whatever the rest of this class, that's not going to be on the quiz today. Don't worry. So suppose we want to solve this triangle with two sides. And we already know that's 90 degrees. And let's see, this side is 7, this side is 5. And we want to know the hypotenuse, we want to know the angle measure, and we have two angles we don't know. How do we solve this? Well, the hypotenuse is always easy to find if you already know two sides. So the hypotenuse, let's call it C. So C squared equals 5 squared plus 7 squared, right? The hypotenuse squared is always the sum of squares of the legs. And from here, we can figure out C is going to be square root of 25 plus 49. So that's going to be, I don't know, 50, 75, 74. Which is not divisible by 2, by 4, I think. So I'm going to leave it there. So that's C, square root of 74, the hypotenuse. But how do we find angle theta? Well, from here, you can use a few things. You can use tangent, because we have all sides now, cosine or sine, it doesn't matter. Let's suppose I'm going to use this side opposite from the angle theta and this side adjacent. So tangent theta equals opposite 5 over adjacent 7. And how do we find the angle theta? That's where we're going to use inverse tangent on both sides. On the left side, it's okay to cancel inverse tan and a tan because we know that theta is going to be small from 0 to 90 degrees because it's going to fit into the range given by the inverse tan, which is going from negative pi over 2 to positive pi over 2. So I don't have to worry about that. So that theta equals inverse tan of 5 over 7. And if I have a calculator, I can figure out what the angle is. At this point, I'm just going to leave it. There's no need to type this in the calculator. And then suppose I want to find phi. Well, if I find a theta, I can subtract it from 180 degrees and then minus 90 degrees to get phi. Suppose I don't want to go down that path. I just want to find phi using trig. Well, again, I can use 5 and 7. So 7 is opposite to phi and the 5 is adjacent to phi. So this is the opposite. This is adjacent to angle phi. So tangent phi is going to be 7 opposite over adjacent 5. And then we just add inverse tan on both sides. So phi equals inverse tan of 7 over 5. Now, a quick note that, as you can see, the inverse tan, you have 7 over 5, that's more than 1. You can have 5 over 7, less than 1. So it really doesn't matter whether the number inside the inverse tan is more than 1 or less than 1, it doesn't matter. But if we have a sine and a cosine, we get the same setup. Suppose the inside is more than 1, then we immediately know there's no solution undefined. Okay, any questions on those? All right, if you don't have any questions, I'm going to go through more examples here. But before that, I want to write down a few important rules. Oh, not quite rules, but more like ways to simplify trig functions and the inverse of trig. So note the following. Composition of trig functions and their inverse. The first one I have is sine inverse of angle x of ratio x is equal to x if x is from, well, let's figure out what the domain x belongs to. Well, let's think about this. So inside the parentheses, we have inverse sine of x. It's inverse sine, so that immediately tell me that the x is going to be the ratio because it's inside the inverse function. Well, if x is a ratio, a trig ratio, then it must satisfy the axis from -1 to +1. Because if it's more than 1, we cannot put it inside the ratio. So that's a ratio. So x is a ratio and the inverse sine of x. And that's going to be an angle. And if we take sine of an angle, that's going to be the ratio again. So therefore, we end up with the same ratio x. And that's only true if x is from -1 to 1. If x is 5, and we immediately know that inverse sine of 5 doesn't exist, so we cannot find the angle. Right? And the cosine of inverse cosine of x, that's equals x if, again, x is from -1 to 1, because, again, x here is the ratio. And tangent of inverse tan of x is equal to x if x is from -infinity to infinity. So that's one set. The second set is if we switch the inverse sine and the sine. So suppose we take the inverse of sine x. That's equals x if x is in, let's think about this requirement. So sine x, we know that x is the angle. And sine x is going to be the ratio. Right? If we just talk about the sine x, the x could be any angle. But because here we're looking for inverse sine of a ratio, and at the end, give me an x. So at the end, inverse sine of a ratio, that's going to be an angle. So this is the angle, just like we begin with the angle x. Now, because this x that we put into sine, and it's also the output of inverse sine, so this x must satisfy the requirement that it's going to go from, because it's an angle, it must be from -π/2 to +π/2, because this x behaves as the input of the sine over here, but also behaves as the output of the inverse sine. So it must satisfy whatever the range is smaller, or the domain, the range. So that's the inverse sine, and the inverse cosine of cosine x, that's going to equal to x if x is in the range of inverse cosine from 0 to pi. Oops. And inverse tan of tan x is equal to x if x is from -π/2 to +π/2. Now, I don't expect you to memorize everything here, but when you see sine, cosine, inverse cosine, inverse sine all together, you just need to think about it a little bit more. Think about whether that's really the angle we're looking for, or whether it's the ratio we're looking for. And then you just have to decide if it's the angle we're looking for, the inverse function, then we have to be very careful because the range is limited. Okay, so let's look at some examples. So example, the first one I have is evaluate inverse cosine of sine -11π/4. So you probably think, okay, shouldn't the answer be Well, I don't know what the answer should be, but let's try to find out. It's definitely not just inverse cosine and sine cancel, right? Because they don't cancel. So what we do with this problem is we just take it step by step. So here we have sine of negative 11 pi over 4. So let's find that part first, and then we're going to find inverse cosine of that. So I'm going to use the unit circle because those kind of problems probably not going to need a calculator. So negative 11 pi over 4. So that's that's positive. So negative pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, 5 pi over 4, 6, 7, 8, 9, 10, 11. So that's a negative 11 pi over 4. And I want to know sine of this. Well, we know we're going to draw a line to the x-axis. This is 45 degrees. Hypotenuse is 1. So we get root 2 over 2 in each direction. And the sine is going to be the y coordinate, which is going to be negative. So the x, I don't need to write the x. I'm only curious about the y coordinate because I'm looking for sine. So that's going to be negative root 2 over 2. So that's this part. So now I can rewrite this as inverse cosine of negative root 2 over 2. And I still want to know what that is, right? And now I'm going to draw a separate unit circle for this part. And I know that inverse cosine of whatever this inside, that's the ratio. Because it's an inverse cosine, so this is going to be the x coordinate. X coordinate is negative root 2 over 2, so this is a negative 1, 0, negative half. Negative root 2 over 2 is a little bit to the left. So this is negative 1/2, negative root 2 over 2 is here, and it's going to be in this, either going to be this angle or it's going to be this angle. Which one is it? So here you can decide already which one to use, or maybe both. Just think about here we have inverse cosine, right? What is the range of inverse cosine? That's going to be the top half of the circle. If you go back to my notes earlier, right? Sine and tangent is going to be the right half. Inverse cosine is going to be the top half. So that we're going to use the angle in the second quadrant. And I mean, it looks, if I draw the circle a little bit better, it should be obvious that this angle corresponding to multiples of pi over 4 or 45 degrees. So that's going to be 1, 2, 3, 3 pi over 4. So that's the angle. Does that make sense? So again, I like to use unit circles on the problems. It helps me understand, but you might have approach that benefit you. In that case, just use whichever approach that makes sense to you. All right, let's look at another example. So suppose we have, so we're going to evaluate cosine of inverse tan of 5 over 12. And this one, I don't know what you remember. For me, I remember, you know, tangent of 45 degrees is 1, tangent of 30 degrees is root 3 over 2, sorry, root 3 over 3, and the tangent of 60 degrees is root 3. So here, 5 over 12 is none of those three good tangent ratios, right? So how do we solve it? In this case, the unit circle is not very helpful. We're going to have to use right triangles. So first of all, we know that inverse tangent of 5 over 12, so this is going to be the ratio. So what we do is we're just going to create a right triangle, and let's call this angle X or theta, doesn't matter, right? And then we know this is going to give us the angle theta or angle X at the end, the angle. But we know that if I have inverse tan of 5/12 equals theta, so that means tangent theta equals 5/12. And I'm just going to manually set 5 to be the opposite side and the 12 to be the adjacent side. Like, I don't know the actual length of both of those sides, but I can just say, okay, because the ratio is 5/12, so I'm going to say the opposite side is 5, the adjacent side is 12. And now I can actually find the hypotenuse 5, 12, 13. That's just a Pythagorean triple that we memorized in the past. And from here, what we're looking for is because the angle theta is inverse tan of 5/12, so we're really looking for cosine theta. And then using the right triangle again, cosine theta is going to be adjacent over hypotenuse 12/13. So a little bit easier in this case. All right, any questions on this? All right, it's 7:01. I don't think I'm going to talk for another hour or hour and a half. So let's take a quick break. So let's see, break and the back. And let's see, 5 minutes is probably too short. So let's take a break for about 8, 9 minutes. So definitely be back by 7:10. And then we're going to talk for another probably 30, 40 minutes before we take the quiz. All right, I'll see you in a few minutes. All right, welcome back. Let's continue with our lesson. I have a few more examples, but probably, well, there's also a couple of new concepts. All right, so example. The next one we're going to do is we're going to evaluate sine of inverse cosine of x over 3. So in this part where x is from -3 to +3, I'm going to use this interval notation. So x is from -3 to +3. So here we have this combination of expressions of trig and inverse trig, but then we have x inside, right? So we cannot really do anything about that. But what we could do, we cannot put in the calculator or anything, but what we could do is just treat x as some number. Suppose eventually we know what it is, but for now it's just a number. So let's find this, see what we get. Well, just like before, if we look at the inner part, this is the inverse cosine of some expression, and this expression, x over 3, that's going to be a ratio. And what we get out of this is going to be the angle. So let's just say, call this angle theta. The theta equals inverse cosine of x over 3. And we can rewrite this as cosine theta equals x over 3. And we're going to use the method we did previously with the right triangle. So let's call this theta. And I don't know the size, but I know the ratio of adjacent to hypotenuse is going to be x over 3. So I'm just going to say this is going to be my adjacent side, and this is going to be the hypotenuse. So adjacent side is going to be x, hypotenuse is going to be 3. And that's what we know based on theta. And how do we find the sine? So, well, because inverse cosine x over 3 gives us the angle theta, so that expression becomes sine of theta, right? And then we can find the sine of theta by using the right triangle, because we already know the hypotenuse. We just need to know the opposite side. Using Pythagorean theorem, this side is going to be 3 squared minus x squared square root. So that's the square root of 9 minus x squared. Use this into this, using this leg and a hypotenuse, we get sine theta is equal to opposite square root of 9 minus x squared divided by the hypotenuse 3. So that's sine theta. The method is basically the same as the previous one. Okay. Any questions? Now there's a second way by using the trig identity sine squared plus cosine squared equals 1, because here we know, remember that we're looking for sine theta, right? But we already have cosine theta. So we can use sine squared plus, so second approach, sine squared theta plus cosine squared theta equals 1. Cosine theta is x over 3, so we get x over 3 squared plus sine squared theta, which is, we're looking for sine theta. So that's going to equal to 1. So we get sine squared theta equals 1 minus x squared over 9. You can come in denominator or you can just leave it. If we come in denominator, that's a 9 minus x squared divided by 9. And now we can find sine theta by taking square root on both sides. We have to add plus minus square root of 9 minus x squared over 9. So that's plus or minus square root of 9 minus x squared over 3. But here you have to be careful. Which one is it, right? Is it the sign positive or the sign negative? So here we have to decide, but based on what we had earlier, the theta is inverse cosine of x over 3. And if you remember, the range of inverse cosine always give us an angle that's from 0 to pi. So if the angle is from 0 to pi, it's going to be in the top half of the circle. So that's where the angle is. For any theta in that range, the sine is always going to be positive because that's a positive y-axis. So sine is positive here. So we don't need the negative. We just drop the negative, keep only the positive. So that's a quick way to tell whether the sine theta is going to be positive or negative. But I personally think the right triangle method is a little bit easier and less messy. All right, any questions on this? All right, so the next thing we're going to do is actually move on to chapter 7 because we talk about a lot of trig identities like a sine squared plus cosine squared equals 1. We're also seeing that 1 plus tangent square theta equals secant square theta. We're also seeing, well, we definitely saw tangent theta equals sine over cosine. And negative angles, so that's a negative angle identity. So that's sine of negative theta or negative x equals negative sine x. Cosine of negative x equals positive cosine x. So we saw all those in the past. We can actually use them to simplify expressions or solve equations. So this is the 7.1. Solve and simplify trig identities / equations. So for example, we want to simplify this one, cosecant theta, cosine theta, tangent theta. How do we simplify this? Well, to simplify, what we do, what I do is I always convert everything back to sine and a cosine because it's a lot easier to work with sine and a cosine because I'm more familiar with them. So cosecant is 1 over sine theta, and the cosine just cosine theta. Tangent is sine theta over cosine theta. And if we start simplifying, the cosine cancel, sine cancel, we just get 1. So that's simplifying. It's a lot easier. Now the second example is that we want to verify to prove this identity or to show if it's true or not true. So the example is secant square theta minus 1 divided by secant square theta equals sine square theta. So that's what we want to show that's true. Now be careful. I want to emphasize one thing. A common mistake is, so when we're given something like this, we have to keep the terms separate. So the terms on the left side, we have to make sure they stay on the left side. The terms on the right side, they stay on the right side. We do not work with two sides at the same time when we try to verify or prove. So do not work with both sides across the equal sign. What I meant by that is that we cannot divide by sine squared theta on both sides, or multiply by something on both sides, or cross multiply. That's not allowed. Do not work with both sides across the equal sign. So you can work with one side, stick there, or work with the other side, stick there until both sides reach to the same expression, but you cannot cross multiply or multiply by the same factor on both sides. So stay with one side at a time. So let's verify this. So let's stick with the left side. So left side is equal to secant squared theta minus 1 divided by secant squared theta. Okay, what can we do? What's the identity that we can use to rewrite this? What we can do is, if you look at it and you just say, I don't know what to do, right? And that's the case, you want to convert everything to sine and cosine, if that's the case. Now, suppose you look at it and you think, oh, okay, maybe I can try this, or maybe I can try that. It's always good to try something. For example, I'm going to show you the second way by converting everything back to sine and cosine in a minute. But suppose, let's say I see that secant square theta is here. I know that earlier I wrote 1 plus tangent square equals secant square. So I'm going to replace that specific secant square with 1 plus tangent square, because it's minus 1. So 1 plus tangent square theta minus 1. And the denominator, I'm going to leave it as secant square theta. So that's going to be 1 cancels. So we get tangent square theta over secant square theta. And I'm looking at it, I still don't know what that is. It doesn't look like a sine square theta. So here I'm going to convert everything to sine and cosine. So that's going to be sine square theta divided by cosine square theta, that's tangent square theta, divided by secant square, so that's a 1 over cosine square theta. And if I multiply by the reciprocal of the denominator, I get sine square theta divided by cosine square theta times cosine square theta over 1. Cosine cancel, give me sine square theta. And that looks just like the right-hand side. So that's the end of the verification, the proof. We're basically showing that the left side eventually equals the right-hand side. So that's a proof. It's not about solving anything. If you say, oh, can I multiply secant square theta to the right-hand side in the beginning? No, so that's definitely not allowed. You cannot multiply the denominator to the other side. It's not okay. You have to keep the sides separate. You cannot move one term from one side to the other side. So that's how we verify it. Like I said, suppose you look at it, you just don't see any trick. Don't worry, it's just, let's just say method 2. We're just going to begin with the left-hand side, and we're just going to convert everything to sine cosine. In this case, everything will be converted to cosine. So that's 1 over cosine squared theta minus 1 divided by 1 over cosine squared theta. And in order to simplify, in the numerator, we have the common denominator. We're going to multiply by cosine squared theta. So that's going to be 1 minus cosine squared theta divided by cosine squared theta divided by 1 over cosine squared theta. And now if I multiply by the reciprocal of the denominator, so that's going to be 1 minus cosine squared theta over cosine squared theta times cosine squared theta over 1. Cosine squared cancels. Give me 1 minus cosine squared theta. And if you remember, sine squared plus cosine squared equals 1. You can either replace the 1 with sine squared plus cosine squared, or you think, well, okay, 1 minus cosine squared equals sine squared theta. And that's equal to the right-hand side. Okay, any questions on this? So one thing to remember, when you try to show something is true, you cannot multiply by, the same fact on both sides, because if you do, you're assuming that's already true, right? You're already assuming the equal relationship. You cannot do that in this type of problems. You have to work with one side until you get to the other side, or you work with one side until you get stuck. Then you move on to the other side, try to work with that side until both sides eventually become the same. But you have to keep them separate. Okay, any questions on this? All right, let's look at another one. So the next example I have is, so we're going to verify if the following is true. So we get sine squared theta minus 1 equals tangent theta sine theta minus tangent theta. Is that equal to sine theta plus 1 divided by tangent theta? So for this one, what we're going to do is, instead of replacing the sine squared theta minus 1 with a negative cosine squared theta, we're just going to leave it for now, but looks at the denominator, looks like we get tangent theta, sine theta minus tangent theta. Looks like we can factor out a tangent theta. That's what we're going to do. So work with the left-hand side. So we get sine squared theta minus 1. The denominator, we can factor out a tangent theta. That becomes sine theta minus 1. And the numerator is sine squared theta minus 1. So we can factor the numerator. So we get sine theta plus 1 times sine theta minus 1 divided by tangent theta times sine theta minus 1. And now we can simplify by canceling out those two factors. So we get sine theta plus 1 over tangent theta. And that's equal to the right-hand side. All right, any questions on this? Okay, if you don't have questions, if you do have questions, please let me know. If not, I'm going to move on to the next one. Now, is the following true or false? And the equation given is cosine theta divided by 1 plus sine theta equals 1 minus sine theta divided by cosine theta. Now you probably think, okay, let's cross multiply. Absolutely not. Remember, you cannot work with both sides. You have to keep them separate. So we're going to pick the left side, or the right side, doesn't matter. So let's see, we begin with the left-hand side. We don't know if this is true or false. So let's say we begin with the left-hand side. So we get cosine theta divided by 1 plus sine theta. Not much we can simplify. The common trick is that we're going to multiply by the 1 minus sine theta to the numerator and denominator. And the numerator is just going to be cosine theta, 1 minus sine theta. And the denominator is going to be 1 minus sine squared theta. Okay. Anything we can simplify? Well, here we have 1 minus sine squared. We know that sine squared plus cosine squared equals 1. So the denominator is just going to be cosine squared theta. The numerator, for now, we're going to leave it 1 minus sine theta. And now I can simplify the cosine theta from numerator and denominator. I get 1 minus sine theta over cosine theta, which is the same thing as the right-hand side. All right, let's look at one more example of this type. So again, we want to know true or false. Want to verify this equation, see if it's true. So we get secant theta plus tangent theta divided by cotangent theta plus cosine theta. Is that going to equal to secant squared theta? We always work with the complicated side, in this case, just left-hand side. So that's going to equal to, I'm going to convert everything to sine and the cosine. because it's easier for me that way. You can convert everything in terms of secant if you like, because the right-hand side is secant. But for me, I'm not going to take that approach. So secant is 1 over cosine theta plus tangent is sine theta over cosine theta. The denominator is going to be cotangent, that's 1 over tan or cosine theta over sine theta, and then plus cosine theta. Now we just have to try to simplify both numerator and the denominator. Numerator, easy, just become 1 plus sine theta over cosine theta. The denominator, we have to be careful. We're going to add we have to combine the terms there. So we're going to multiply the numerator denominator of cosine theta with sine over sine. So that's going to be cosine theta plus cosine theta sine theta divided by sine theta. It's just getting a little bit messier, but that's fine as long as we're careful. So we get 1 plus sine theta divided by cosine theta. Divide by a fraction, you can think about it as multiplied by the reciprocal. And in fact, we can try to factor this part as we multiply by the reciprocal, right? So sine in the denominator goes to the numerator now. And we can factor out a cosine theta here, 1 plus sine theta. And now if we simplify everything correctly, we can cancel out the 1 plus sine theta factor. And nothing else cancels. We get sine theta equals cosine squared theta, which is 1 over cosine squared, that's secant squared. So they get sine theta secant squared theta. As you can see, this is not equal to the right-hand side. So that equation given is false. All right, any questions on this part? Okay, all right, I have 2 equations that I want to solve because we do want to use those to solve equations sometimes. So equations to solve this equations. So the first one I have is 4 cosine squared theta minus 1 equals 0. And we want to solve this, means we need to find the angle theta. We're just going to solve it like we normally do with the quadratic equation. So we need to isolate the cosine squared, and then we need to isolate cosine, and then at the end, the angle. So we're going to move the 1 to the right side, and then we're going to divide by 4. So we get cosine squared theta equals 1 divided by 4, so 1/4. And from here, we're going to take square root. So cosine theta equals plus minus square root of 1/4, which is plus minus half. So I'm going to write down 2 equations. Cosine theta equals 1/2, or cosine theta equals negative 1/2. And we're going to solve each one separately. So cosine theta equals 1/2. So theta equals the inverse cosine of 1/2. And if you remember that the unit circle, if you have cosine of an angle equals half, obviously you probably have it memorized. If not, we're just going to draw half. And the cosine is going to give me angle in the inverse cosine is going to give me angle in the top half. So it's going to be this angle. How big is this angle? Looks like it's 60 degrees. So theta equals pi over 3 or 60 degrees. Now from the second equation, we can also solve for theta, which is inverse cosine of negative half. Again, borrowing the unit circle, the angle should be in the top half of the circle. So cosine of an angle equals negative half, so x is negative half. So it looks like it's this angle. And that angle, if I'm guessing it correctly, this is 30 degrees. So 30 plus 90, 120 degrees. So that's going to be 2 pi over 3, or 120 degrees. So in this case, we get two angles. But obviously, if the question says, solve this equation for theta is from 0 to 2 pi, that means we're going to use all 4 angles. But here it doesn't tell us what angle is in. We're just going to have to use the definition of inverse cosine to get the correct angle. Okay, let's see. Okay, I'm not going to go through the second one. It's the same, basically. All right, any questions at this point? All right, the next one, just a couple identities that you have seen before, but you probably don't have it memorized. You do need to have it memorized because it's going to be very handy when you need it and in calculus. So this is the next section, 7.2, which is sum and difference. We're not going to finish it today. I'm just going to get started of angle. Sorry, sum and difference of angles. So you probably remember sine. Suppose we have angles A and angle B. So this is angle B, right? And the sine of A plus B, so that's going to be sine A cosine B minus cosine A sine B plus, sorry. So that's sine. And if we have sine of angle A minus B, so that's going to be sine A cosine B minus cosine A sine B. Now, the way I try to remember is that if you have sine, then you must begin with sine. And for sine, it's going to be different in there, but then the actual operation between those two terms is always going to be the same. So if you begin, oops, I should draw it this way. So it's going to be the same operation. So if you begin with addition of 2 angles, you're going to end up with addition of 2 terms. If you begin with the subtraction, you get subtraction. So that's sine. And similarly, cosine angle A plus B. So that's going to be cosine A cosine B. It's going to be minus sine A sine B. I hope I'm not memorizing it wrong, but last time I checked, this is correct. So for cosine, if you begin with cosine, you begin with cosine. It's going to be 2 cosines, so they're the same trig ratio, but then the operation is going to be different. And if you have cosine A minus B, so that's going to be cosine A cosine B plus sine A sine B. So those are the sum and the difference of angles. Okay, so how we use this? Well, a common one that being used is, for example, we're going to find cosine of 15 degrees, the exact value. No calculator. So if you put in the calculator, you get an estimate, right? So how do we find the exact value of cosine 15 degrees? Well, cosine 15 degrees is not one of the nice angles, right? It's not multiples of 30, 45, 60. So we're going to have to use the combination of them. So for example, so since 15 degrees is equal to 45 degrees minus 30 degrees, we're going to use this difference. So that becomes cosine of 45 degrees minus 30 degrees. So that's going to be using the difference of angle formula. So that's going to be cosine 45 degrees cosine 30 degrees minus sine 45, plus sine 45 degrees sine 30 degrees. And then we know what cosine 45 degrees is and a cosine 30 degrees. So that's going to be cosine 45 degrees is going to be root 2 over 2 times cosine 30 degrees. So that's going to be root 3 over 2 plus sine 45 degrees root 2 over 2 sine 30 degrees, which is half. So if you simplify everything, we get square root of 6 over 4 plus square root of 2 over 4. So that's a square root of 6 plus square root of 2 over 4. As you can see, it's an irrational number. If you put it in the calculator, you only get an estimate. You don't get the exact value. And this is very useful because if you have any multiples of 15 as the angle measure, you can always use this approach. So 15, I mean, obviously 45 we already know, but when we have 75, you can use the same approach. All right, so as a final example, before we take the quiz, I'm going to give you this one. So find the exact value of sine. Inside the sine, we have inverse cosine of 1/2 plus inverse sine of 3/5. It looks like, you know, it's complicated because you have a sum of sine, so you have a sum of those two inverse functions, but then you want to find sine of them. But it doesn't matter, right? Because inverse cosine of 1/2, so that's going to give me an angle. And this inverse sine of 3/5 is going to give me another angle. So basically, we're looking for sine of angle 1 plus angle 2. So to write it out, what we're going to do is just use the sum of angle formula. So that's going to be sine of the first angle, which is inverse cosine of 1/2. So that's sine A, and then cosine B, so cosine of inverse sine of 3/5, plus cosine A, so cosine of inverse cosine of 1/2, and then times sine B, so sine of inverse sine of 3/5. So that's the sine A cosine B plus cosine A sine B. I probably use A and the B instead. So this is a sine A times cosine B plus cosine A times sine B. All right, so we just have to kind of redo what we did earlier, right? 4 times. In fact, 2 of them are relatively easy. So let's see, one at a time. So for the first one, I know that inverse cosine is 1/2. So that means I'm looking at this part. So that means the x coordinate is 1/2. So what's my angle? The angle is going to be 60 degrees. So this is going to be sine of 60 degrees, pi over 3, and times cosine. And the inverse sine of 3/5 is not a nice angle that we're familiar with, but we can use. So suppose this is theta, So this becomes cosine theta. So let's see what cosine theta should be if we use the right triangle. So sine is opposite over hypotenuse. So opposite is 3, hypotenuse is 5. So the other adjacent side is going to be 4 using Pythagorean theorem. So cosine theta we can find using the right triangle below. Now, what about cosine of inverse cosine of half? Well, because the half is between -1 and the 1, right? So here we just get half by itself. We don't get anything fancy. Or you can, if you want to take a couple of steps, so that's become cosine of pi over 3, which is just half times sine. Again, inverse sine of 3/5. We're looking for that's the angle theta, so sine theta, which is still going to be 3/5. So now what we have is sine pi over 3, so sine 60 degrees. That's going to be √3 over 2. Cosine theta using the right triangle, that's a 4 over 5, plus cosine pi over 3, so cosine 60 degrees is 1/2, and the sine theta is 3 over 5. You can always, at this point, you can just say, okay, because half is between -1 and a 1. Same thing, 3/5 is between -1 and a 1. So this is just going to be equal to half. This one is equal to 3/5. So at the end, we have to simplify everything with the denominator 10. So that's going to be 4√3 plus 3 over 10. I just want to use this example. It sort of bridges two concepts. One is when you have sine, the trig and the inverse trig together, how do you find it? But when you have sine of sum of two angles, how do you find the exact value? You just apply the sum of angle formula first, and then you just work with each part. Any questions on this? All right, any questions about today's lesson or anything that we haven't talked about? For example, from reviewing for the quiz. It's almost 7:50. Again, I don't think you're gonna run out of time. I don't think time is the issue with this quiz, just like the previous quiz. To be honest, I think it's plenty time to work on the problems. So please submit it in time. If you have extended time, you have accommodations, that's totally fine if you submit it a little bit later. But again, I'll just let you decide. I don't think you're going to need really the extra time. But anyway, let's see. So if you go to home page, and then this is a quiz 4, I'll click on assignments, quiz 4. All right, let's see. All right, any questions before I make the quiz available? All right, then. Just like before, so I'm publishing, so the quiz should be available now. Take a quick look. If it's not available, let me know. And it has 3 problems. Just like before, when you finish, upload the solution. Again, don't stay on Zoom. There's no need to stay here. In fact, I'm probably going to go grab some food, but I'll leave it open, so you can ask me questions if you do get stuck on any of the problems. All right, take care, everyone. I'll see you Wednesday.
Thank you.
All right, bye-bye.
Thank you.
Yep, bye.
Thanks.
All right, take care.
You too.
Yep, bye.